See, in this problem, it is given that an ideal gas of density rho equal to zero point 0.2 meter, 0.2 kg per meter cube enters a chimney of height h. So at a rate 0.8 kg per second. That is the mass flow rate. Mass flow rate we know rho AV, density into cross section into speed. The so mass flow rate is 0.8. It enters from the lower end and escapes through the upper end as shown in the figure. Cross section area of the lower end is A1 and upper end is A2. Pressure and temperature of gas at the lower end are 600 Pascal and 300 Kelvin, while temperature at the upper end is 150 Kelvin. The chimney is heat insulated, so the gas undergoes adiabatic expansion. Take G is 10 and ratio of specific heat, so gamma is 2. So ignore atmospheric pressure. Which of the following statements are correct? The pressure of gas at upper end. So see, first of all, we can equate the mass flow rate. Rho 1 A1 V1 equal to rho 2 A2 V2. And then as it is adiabatic process, P V to the power 2 equal to constant. That gives, if you substitute, so temperature is proportional to rho density, because see here what I have done. So P is nR T by V into V square equal to constant. So T into V is constant and V is proportional to 1 upon density. So T is proportional to rho. And let us find a relation between temperature and pressure. So we do it like this: pressure into, in case of volume, nR T by P, so that square equal to constant. So T square is proportional to V. So let us find T square is proportional to P for pressure. Now pressure of gas at the upper end, so we can equate that T square by P, that is T1 square by P1 is equal to T2 square by P2. So for the lower end, T1, so 300 square by P1 600 is equal to T2 square. T2 is given 150 square by P2. So P2 is pressure at the uppermost end. So that implies P2 is equal to 600 into half square, that is 1/4. So that is 150 Kelvin. So 150 Pascal rather. So pressure at the topmost end, P2 is 150 Pascal. So obviously this is not correct. So option A is not correct. Now velocity of the gas at the lower end of the chimney and the upper end is. So for that we go back to the first line what you have written. Rho 1 A1 V1 equal to rho 2 A2 V2, and both are equal to alpha, that is the given as mass flow rate in kg per second. So rho 1 is 0.2 into A1 is 0.1 into V1. So rho 1 A1 V1 equal to alpha. So let it be, so V1 is equal to 0.8. So therefore we can find V1. So V1 is equal to 0.8 divided by 0.2 into 0.1, that is 4 by 0.1, that is V1 is equal to 40 meter per second. And see, at the topmost point, density, as you see, temperature is proportional to density. So as the temperature becomes half at the uppermost point, at the lowermost point it is 300 Kelvin and uppermost point 150 Kelvin. Lowermost point density is 0.2, uppermost point density should be 0.1. So we know rho 2 is 0.1, and you know A2 is 0.4 is given. So rho 2 A2 V2 is also equal to alpha. So rho 2 A2 V2 is also equal to 0.8. So therefore V2 is 0.8. So it becomes actually 20 meter per second. V2 is equal to 20 meter per second. So this option is correct. B, that is velocity of the gas at the lower end is 40 and upper end is 20. And also we can see that option C, which says density of the gas at the upper end is 0.05, that is incorrect. So we can cancel off this. Now the next part is to find the height of the chimney. So we know that Bernoulli's equation is applicable for the incompressible fluid. Here the fluid is not incompressible, it is rather compressible, density changes. So we will use the Euler's equation, which we have derived before the Bernoulli's equation. That is, we have shown that Bernoulli's equation is special case of the Euler's equation. If you want to know about this, so you can see my other video on fluid mechanics, derivation of this Euler's equation. So you know it is dP by rho plus v square by 2 plus g dz is equal to 0. This is the Euler's equation, and so this one. So we can substitute in this Euler's equation. Now pressure and density, so you know PV square equal to constant. So P by rho square equal to constant. So let this constant be K. So P by rho square equal to constant. So therefore P is equal to K times rho square. So we can write like this. So dP is K into 2 rho d rho. So we can write here like this: K into 2 rho d rho divided by rho plus v square by 2 plus g dz is equal to 0. So here this will cancel out. Therefore we can write 2k integration of d rho plus so it was actually dP by rho, sorry, it was v dv, sorry, extremely sorry. This was not v square by 2 will come after integration. So v dv, this was v dv. Okay, so after integration you get v square by 2. So half v2 square minus v1 square plus g into z2 minus z1, that is h actually, z2 minus z1 is h. Now so here, so integration of d rho, so you know 2k into rho 2 minus rho 1 plus half v2 square minus v1 square plus g h is equal to 0. So now we can write this 2k, or write this k as 2 into k is pv square. K is equal to pv square, or k is equal to p by rho square. See, here it is given p by rho square. P by rho square equal to k. So we can write any, say, p1 by rho 1 square into rho 2 minus rho 1 plus half V2 square minus V1 square plus GH is equal to 0. So now we can find out H from here. Therefore, H is equal to 1 by G, that is so half V1 square minus V2 square plus 2 P1 by rho 1 into rho 1 minus rho 2. Now we have to substitute the values here. So after calculating, at least I know that, seen that this doesn't come out to be 590. So we can cross off this option as well. So only one option is correct, that is B.